Okay, sorry for that interruption. I don't know, my computer was just my iPad was just playing up there. Sorry about that. Hopefully that won't happen again. So just to remind, we're talking about this notion of relating this to model selection, where we're trying to choose we're trying to determine the S features or covariance that are relevant to the response. And there are prior classical work when P was small, which involved kind of AIC or BIC. And, from the regularization perspective, that means that R of B is just norm of B0. AIC and BIC, the only difference between them was that you chose lambda a little bit differently. So, so for AIC, we had that lambda equals something like square root of n log n roughly, and I think there might be a 2 there, but I don't know exactly. And then for I think for AIC it's just it's 2 times n or something like that, but you can check that yourself. And for BIC, lambda equals something like, you penalize a little bit more. It's something like n times square root of log n. And so, this does fit into our regularization framework, but computationally not feasible when n is large. When P is large, since so we're effectively searching over P choose S subsets. And so you can imagine that if P is like 100,000 and S is like 100, how big that number is. And so, what these approaches effectively involve doing, AIC and BIC, when you're trying to minimize the sum of that plus the L0 norm, or L0 norm that's not a norm, is that you're effectively just plugging in each of the P choose S different models, and then picking the one that minimizes that objective. And that isn't computationally feasible at all. Is convex, and as it turns out, it's the best convex approximation to B0. So that's why the L1 penalty has kind of gained a lot of interest, and there's been a lot of work on it for the last 20 or so years. Because the way you can think about it is it's computationally scalable model selection. So really, like, this is this particular idea of like L1 regularization or the lasso is really what made this sort of notion. If you've heard of the notion of high dimensional statistics, this kind of really made that very popular, because it provided a way that you could kind of scale up the notions of model selection, where you're trying to search over P choose S models. This provided a way to do it in a computationally very tractable way, because of the fact that R of B is convex, and we've sort of learnt already that nice things happen with convex objectives. And we're going to see that it gives you kind of quite a nice algorithm today, and because we have convexity, we can say a lot of nice things about those algorithms. Okay, and I just wanted to reference the So there's a 1996 paper by Rob Tibshirani, and that I think is, if you want to learn more about the lasso, that's one of the more widely cited papers of the last, you know, 20, 30 years, because of how much popularity high dimensional statistics and the lasso has gained. So I kind of wanted to point you to that reference. I've given just a very quick overview of a kind of why it's, the purpose behind it, because I think it's important before we dive into it, just to give a broader context to why we're looking at that why we're looking at this in particular. So you should kind of think of the idea that if P is large and you want to do model selection or impose this notion of sparsity, that this is where the lasso has become a really, really powerful tool and idea. Okay, so now we're going to tie this back to our framework. So let's talk about where it fits in the context of our statistical framework. Yeah, and I should also mention that if you're not familiar with AIC and BIC, I encourage you to just read about that, because there are R functions that allow you to use AIC and BIC, and so when your P is like 10 or even 100, they're pretty good and they work pretty well. But if we want to start scaling to sort of hundreds of thousands and more, or thousands or hundreds of thousands, you really can't use these classical approaches. But I think it's still useful to know a little bit about them. So let's again talk about our statistical framework. So once again, we're in this supervised setting. I equals 1 to n, and once again we're going to use this this convenient matrix vector notation to express the data, because we're going to talk about it in the context of the linear model. As I mentioned, it's typically easiest to understand what's going on with these methods through the linear model. Okay, and our statistical model here is we're again going to have this linear model, which we've seen throughout the course, but we're going to impose the extra sparsity assumption. So you can also think about this as what we saw in the previous lecture, and what we've generally seen, that Y is a multivariate normal with mean xb and variance sigma squared over n. And then we're also going to impose an additional assumption of sparsity, which is this notion that many of the coefficients are coefficients are not zero. So we're assuming that S here is less than, or obviously, I guess I don't need to state that because that's trivially true, but this S is going to be kind of an important sort of parameter in what we talk about today. And we're also going to make this convenient assumption that that we did in the previous lecture. Okay, and that again is going to be useful for analysis, And but as I mentioned in the previous lecture, a lot of the insights that we deduce from this example carry over to more general design matrices X. But we're just gonna because the main idea is to get a sense of what's going on. We're going to use to impose this assumption. So I'm gonna the main thing that makes that's distinctive about our approach is that we're going to use the L1 penalty. So once again, we have our typical least squares loss, but now we impose this this L1 penalty, and so we're going to try. So this should be an element of because we don't necessarily know that it's unique. We'll see later whether it is or not. In the case where we make this assumption X transpose X over N, it turns out that it is unique. But in general, for general X, you need rank X. You need rank of X equal to P to be unique. I'll talk about that shortly. And so this is what we consider, and then we're going to address the question in this lecture. How do we find B hat L? Because this is not quite as simple as the case of ridge regression, which we saw, where all of our where things are worked out to be nice and linear. This is clearly not going to be linear because the L1 norm, when you we'll talk about differentiating it shortly, it's not it's actually not differentiable, and you certainly aren't going to get anything linear there. And so we're gonna there's many different algorithms because there's been such a wide body of work. Just to give some insight, I'm just going to talk about one which is referred to as soft thresholding. And that's also related to another algorithm which is called coordinate descent, which is widely used. But I'm gonna sort of talk about that shortly. And then analysis. And then we're going to address the specific question of, what can we say about and we may get to this today, but we may not. And this is going to be in terms of like the parameters S, P, N, and sigma squared. They're sort of our key parameters of what can we say about this. So the main focus of today is going to be algorithmic. So one thing to note is norm B1 and y minus xb squared are both convex. So that makes minimization kind of a nice thing to do, because so therefore any local minimizer is also global. And so this is one of the one of the really nice properties of convexity. So we know, we've already seen that y minus xb squared is convex. So B1 is convex because it is a norm. So I'm gonna, if you're not aware of all the properties of norms, norm of B1 is a convex function because it's a norm. So that's something that you can also kind of check yourself. The norm satisfies the triangle inequality and scaling and all those nice properties, and that is what you need to ensure convexity. But you can convince yourself of that, and we're also obviously assuming that lambda is bigger than 0. But there's this next natural question is it unique? And the thing to note here is that B1 is not strongly convex, or not strictly convex. So norm of B1 is not strictly convex. And remember, for ridge regression, we had that the norm of B squared was strictly convex because if you took its double derivative, it was 0. This is not strictly convex in any sense because, well, it's not even differentiable. We'll talk about that shortly. You can actually find multiple ways to solve this. So this is not in any way this is not strictly convex. And to ensure single solution, or to ensure, I should say, unique solution, you need the norm of y minus xb squared to be strictly convex. And this is true if and only if rank of x equals p. So, we talked about that condition for least squares, that least square is only unique if you can kind of invert that matrix x transpose x. And so you need that to be invertible. So this is, obviously true if x transpose x over n equals the identity, because obviously you can invert the identity, so that's trivially true. But in general, particularly when p is very large, so in many settings you'll actually have p bigger than n. And so one thing to note is that this is not true in our particular case here, but if p is bigger than n, rank of x has to be less than or equal to n, which is obviously less than p. So therefore not strictly convex. And that's in the this is referred to often as the high dimensional regime. So typically you're actually not going to get a strictly convex objective. And in fact, so for high dimensional problems, your solution actually isn't usually unique. But the good thing about it is, even though the solution is not unique, like all of the local minimizers you have is still global because it's convex. Okay, but note that in our case, x transpose x over n equals the identity. So I'll just repeat that again. So B hat L is unique. So we can say that we can convert that element to an equal. So this is the objective. Okay, so a natural, now we address the more challenging question of how do we find what would you do typically? So typically you'd say that usually you'd say that you just set the gradient to be 0. So we know that the gradient of that quadratic we've computed many times, and that's easy. But then you have to ask, what is gradient for norm B1? So now let's think about this question a little bit more. So norm B1 here is and think about the case when, so if p equals 1, it's just the absolute value, right? And so if you plot that, what does that actually look like? So B versus the absolute value of B, it looks exactly like this. And one thing to note is that it's clearly not differentiable, right? Because we have this at B equals 0, right? So clearly this is not differentiable because we have this, point of non-differentiability at 0, and that kind of, makes this not differentiable. So you can't actually take this gradient. Okay. So for convex functions that are not differentiable, you need the notion, a generalized notion of a subgradient or subdifferential. And so what that is just, so what typically is a gradient? It means that if you take a tangent, then if you take a tangent, or if you take a tangent to that function, what does it look like? And so for convex functions, you need a notion of a subgradient or subderivative. And so just to, again, I'm kind of going through a lot of things about convexity very quickly. So I kind of encourage you, if a lot of this is not making sense and you want to learn more, to just read a little bit more about convexity and properties. So for convex functions, one of the properties of convex functions is that all tangents lie below the function. Okay, so basically what you're saying is that because the double derivative is bigger than 0, it means that the rate of change is sort of faster. And so another way to actually express that is that if you take a tangent point, then, sorry, let me... If you take if one function that we know is convex is the quadratic, and so if you take kind of a tangent to that, which is you just sort of at a point you draw the line, it's always below the function. You can check that for any point, right? So this is kind of the property of convex functions, and this is one of the reasons why they have why all zero gradient points are in fact minimizers, because this is related to why all of the tangents have to lie below it. If you have a function that kind of goes the other way, then you're not going to see that. So for example, if you take if you kind of take a tangent point here, so this is not convex, and note that gradient 0 point is point is actually maximum in this case. Okay, so again, I'm kind of going through things really quickly. So if you want to kind of get a more rigorous understanding of this, I encourage you to kind of look up convex functions and convexity. And there's some good books on convex optimization that if you want to read more, I can point you to. But I'm just kind of trying to like cover the material that we need for this course. So going back to the L1. And the notion of subgradients. So at each point is below the function. And so this always exists for convex functions. So for example, for this L1 function, or the absolute value, we can see that for b not equal to 0, we're kind of asking this question of, find a subgradient or subderivative of norm B, and then we'll call that Z. And so we can say that for b not equal to 0, this is actually a pretty nice and differentiable function. We'll say, so we know that z is just equal to the sine of b. So what that is just, it's 1 if b is bigger than 0, and it's -1 if b is less than 0. So the critical question is what happens at b equals 0. So for b equals 0, there's actually many choices you can make for the subderivative, because you can see that, this is below the function, this is also below the function. You can kind of go anywhere up to this line. And so if you just let z be less than or equal to 1, because the gradients of all of these lines here that I draw are less than or equal to 1, this is a and in the next lecture, I'm going to provide a more rigorous definition. I wanted to just kind of provide intuition first for where this is coming from. So we're just going to let z be subderivative of the absolute value of b. So we know that z is and so we know that z is equal to 1 if b is bigger than 0, -1 if b is less than 0, and we'll say we know that it's in -1 to 1 if b is equal to 0. It could be any number, so there's actually many gradients. So there's many subgradients. So the gradient's always unique, but the subgradient need not be unique. And all convex functions have at least one z that you can choose. So we're just going to let z denote that. And so going back to what we're talking about here, let zj be the subderivative of the absolute value of bj. therefore the subderivative of the L1 norm is z, which is going to be a p-dimensional vector, because remember this is a p-dimensional function, which is just going to be z1, z2 up to zp. So this is an r to the p. We're going to see how that's useful shortly. So therefore, we don't have a gradient for the L1 norm, but we do have a subgradient, and so so we can say that set subderivative to 0. And again, this is all potentially quite new for a lot of you, and you don't need to understand this completely rigorously, but we're going to see sort of how this is useful for solving the lasso. So we want to differentiate, or sub-differentiate, I should just use that term. Okay, so we know that the derivative of the quadratic is easy enough to deal with. We've dealt with that many times before. And then now we have that this is going to be, I'm going to use this term L, z hat L, so and we know that this whole thing should be equal to 0. Okay, and so remember that we have this notion that we need to keep in mind that z hat L is equal to 1 if b hat L j is greater than 0. It's negative 1 if b hat L j is less than 0, and it's 0, or it's sorry, it could be any number between negative 1 and 1 if b hat Lj equals 0. Okay, so that's what we have, and we know that any solution satisfies that. And so now what we're going to do is we're going to now use our assumption, which is going to be very useful. So x transpose x over I, n over I equals I p by p. And I'm also going to introduce this notation here. So let y tilde be x transpose y over n. So this is actually an r to the p. So we're moving kind of y into this data domain, or this should be x transpose y over square root of n. And why are we doing that? Because so the reason why we're doing that is that y tilde equals x transpose y over square root of n, which equals to xb plus epsilon over square root of n. And so you can kind of express this as you can express this as x transpose x b over square root of n plus epsilon over square root of n. And using this, let me just see if that makes sense. So using this definition, this is just exactly equal to square root of n times I times b plus epsilon over, sorry, this should be x transpose over square root of n. And we know that x transpose epsilon over square root of n is distributed. From the previous lecture, we know that that's distributed sigma squared I p by p. So you can think about this as being square root of n times b plus epsilon tilde. And so where epsilon tilde is mvn 0 sigma squared I p by p. And so why that's useful, so we have that sorry. And so what that gives us is this is now going to be and so we can re-express this now as n times b hat L and then plus or minus square root of n times y tilde plus lambda z hat L, and that whole thing should be 0. Okay, and then if you want to simplify that further to kind of make it to make that look nicer, we're going to get n b hat L minus b and then minus square root of n times epsilon tilde plus lambda z hat L equals 0. So a lot of kind of nice things happen here, and that's going to kind of lead us to our soft thresholding algorithm, which I'll get to shortly, and that gives you kind of a nice solution. So we can say that b hat L equals to b hat L equals b plus epsilon tilde over n, and then minus lambda z hat L over n. Okay, and this whole thing here is you can express that as this whole thing here is y tilde over square root of n. So you can say that b hat L is equal to y tilde over square root of n minus lambda z hat L over n. So this gives you kind of a data dependent estimator. But then there's this question of how do we convert that into an algorithm? So we still have this kind of annoying z hat here. So this is nice because things are like kind of looking closed form, but we still have the z hat L to deal with. So this is where we kind of use the, there's three cases here, right? So if b hat L is bigger than 0, then we know that z hat L equals 1. Okay, and then, so this is case, sorry. If b hat L is less than 0, we get z hat L equals -1. And then if b hat L equals 0, I guess we don't really know what z hat L is, but it should be between -1 and 1. But it turns out that we don't really need to know what it is, because what we can then do is just plug it in. So then we can say that b hat L equals y tilde over square root of n minus lambda over n if b hat L is bigger than 0. And it's y tilde over square root of n plus lambda over n if b hat L is less than 0. And obviously it's it equals to 0, obviously, if b hat L equals 0, okay? And so this kind of gives you a nice closed form then, because what that says is that so this gives you this actually gives you now a closed form expression for beta hat L. So if y tilde over square root of n minus lambda over n, if that thing is bigger than 0, then beta hat L equals 0. If y tilde over square root of n minus lambda over n or plus lambda over n is smaller than 0, yet beta hat of L is this is yeah, so this is kind of another way to express it, is that so let me just express it this way. I think this is the easiest way to express it. So we're going to turn it now into conditions on the data, and we'll go through this in more detail in the next lecture, but I want to get to the end of this. So what we're saying is if y tilde over n is greater than lambda over n, then we have that b hat L equals y tilde over square root of n minus lambda over n, and we know that that's bigger than 0. And if y tilde over square root of n is less than negative lambda over n, so it's kind of then we have that b tilde of b hat L is, and so this is going to give you kind of a negative answer. And then obviously if so if y tilde over square root of n is between the two values, so it's between negative lambda over n and or if it's if it's between these two values, then we have beta hat L equals 0. Okay, so this actually gives you kind of a way to estimate, and this is what's referred to as the soft thresholding operator. So another way to express this is that your data is like your y. So let your data be your y over square root of n. So you have these two limits of lambda over n and then negative lambda over n. And so what your algorithm, what your b hat L is essentially it's essentially this function. So it's a linear function up until negative lambda over n, and then it thresholds things to 0, and then it goes back once you go above lambda over n. So you can see that it thresholds to 0 if the absolute value of y tilde over square root of n is so let me again just say that I've kind of done this component, I've done this component by component. So this is certainly true, but let me just because we've diagonalized everything through this assumption, this holds one component at a time. So this is one of the other things that I forgot to mention. Sorry about that. Okay, so if we look at if y hat j of is less than or equal to lambda over n, then set b hat lj equal to 0. So if the absolute value is bigger than lambda over n, b hat lj will not be 0. So it'll be positive if y hat j is positive, but it has to be positive and bigger than this threshold of lambda over n. And it has to be kind of, and if it's less than negative lambda over n, which means it's larger than a threshold and a negative number, it'll be negative. Okay, so I'm going to go over this in more detail in the next lecture and also look at the question of how do we choose lambda, and then we're going to kind of turn that into how do we provide some analysis on the mean squared error. Okay, so I'll clean up a few of the concepts that may be a little bit fuzzy today in the next lecture, because I agree that it's a lot of new things to kind of take in today. But yeah, hopefully it'll be clearer with when I go through lecture 13. The main point of today is just to get a sense for what this highly nonlinear estimator is actually doing. Okay, thanks very much.